All right, Pre-Cal 11, welcome to section 4. This entire section is dedicated to quadratic functions. So fancy math words that mean U-shaped graphs. We've seen these before. We call them quadratics or polynomials of degree 2. So these are quadratics that you've seen of this form. ax squared plus bx plus c. Now all that means is what? It means a polynomial, or sorry, not a quadratic like x squared plus 5x plus 6, right? My a term in this case is a 1. But we also saw ones where our a term changed. 2x squared plus 4x plus 7, for instance, right? Those are all the general form of a parabola because they are power 2, right? That's what makes it a parabola. Now, you'll get more into that in maybe some later videos for this course, but definitely in Pre-Cal 12 if you head there. Now, the a value is quite important with respect to what the graph looks like. Okay, the a value is, the number in front of the x squared. If a is greater than 0, which means if a is positive, you have an upwards opening u. So the vertex is a minimum. If a is less than 0, so negative, you have a downward opening graph. So your vertex is what we call a maximum, because it's a maximum point. Now, this type of graph you see often in a relationship to anything that is affected by gravity on Earth. If you think about, pointing a cannon up or shooting a potato gun or throwing a baseball as high as you can in the air, it doesn't really matter. Any sort of vertical trajectory, an item is going to start at its starting point. It's going to travel up with upward velocity until it reaches its peak, where the upward velocity matches gravity, and then it's going to travel back down to the ground. And the thing is that amount of time and that amount of time are equal. It is a symmetric function, which we will talk about a little bit further down. So you'll see here I said quadratic functions are the backbone of many day-to-day situations because we live on Earth and gravity affects many, many things. You'll see everything flies through the air, makes a parabolic arc. And then when you get to calculus, you start to see the applications of quadratics, like water flow, support cables, tension. And when you get into engineering and higher levels of physics and chemistry, it's rates of change, which is often described through quadratics. So I know that sounds exciting, but that is where we are going. So, definition of a quadratic function is exactly what we just talked about. It is a function in the form ax squared plus bx plus c. A, b, and c are real numbers, which means they can be fractions. They can be irrational numbers. It doesn't matter. They just can't be what we call imaginary numbers. Now, imaginary numbers are numbers that you may see in Calculus 12 or Pre-Cal 12 if your teacher's feeling energetic. But basically, an imaginary or a complex number is a number that cannot be written as a square root. So essentially what we're talking about is we're talking about the square root of a negative number. So everything else, we're totally okay, which really doesn't eliminate much, right? All real numbers, we have tons of options. So keep that in mind as we go, but we're going to look at some very specific ones here as we begin our journey. Now what you see here is they're real numbers, but a doesn't equal c. I will confirm at a later moment, but I'm almost certain that that might be a slight typo. A doesn't equal c. A can equal c. That's fine. What a can't equal is a cannot equal 0, because if a equals 0, we don't have a quadratic anymore. So make sure you make that adjustment. That's fine. Okay, a can't equal 0. So the simplest quadratic is the form y equals x squared. And I'm going to give a little bit of extra info here because for me it's super helpful. So here we go. So you'll see with the quadratic y equals x squared, this isn't an exact graph of it. I'll show you an exact graph in just a couple minutes, but there are some principles that hold true, and I use this graph because it helps highlight. One, the vertex is at 0, 0. all right, the bottommost point. And then this lovely set of words here, the line of symmetry. That means it is symmetric on either side of that line. So the line of symmetry divides it into two equal halves, and it's at the x-coordinate of the vertex. So here the x-coordinate of the vertex is 0, and we have the axis of symmetry at x equal to 0. And remember that an x equals line is a vertical line. So you have a line of symmetry that cuts through the parabola. This side of the parabola is identical to this side of the parabola. They're just on opposite sides of the line of symmetry. Okay? So, x-intercept, y-intercept, we've seen these things before and they still are calculated the same way. So remember that your y-intercept is where x equals 0. So if you set your equation in this form equal to 0, set x equal to 0, something quite apparent happens, right? You end up with whatever a is times 0 squared plus b times 0 plus c. So really what you end up with is f of 0, f of x, right? But when x is 0 equals c. So c, this number, is your y-intercept. So you can see that the y-intercept is 0 comma c every time. So if we had x squared plus 5x plus 7, your y-intercept is plus 7. So that's why the general form gives it to you so nicely, and it's good to look in that sense. The x-intercept we've also handled before also, right? The x-intercept was when we factored a quadratic, because now the x-intercept is when y equals 0. So if we look at that, why we put so much emphasis in being able to factor these things was you factor that out and it's equal to 0. It tells you your x-intercepts, right? And in this case that I've just drawn in as an example, your x-intercepts are -2 and -3, which is why we covered section 2. We went back into making sure you can factor quadratics no problem, because it's going to jump out at you here in this section. And I don't want to say we take it for granted, but it's just, you got to be able to do it by this point, right? So we call them roots, solutions, or zeros, right? They're solutions to our equation, they are roots, and they are also zeros. And we call them zeros because they make the equation equal to 0. Now the thing is we have 3 different scenarios. If you have a quadratic that crosses through the x-axis, you're going to have 2 solutions, because it's got to go through, it reaches its vertex, and it goes back up. If it sits right on the x-axis, we only have one x-intercept. And if it doesn't go through the x-intercept, or the x-axis, if it's just a v that is positioned with a vertex above the x-axis, right, like if here's the x-axis, then there's just no roots. Now, a little bit of a teaser for you, there's no real roots, but this is where we get those complex numbers or those imaginary numbers that you will eventually learn and study about at some point if you continue on mathematically. So you're going to have one of 3 scenarios, and then just think it's exactly the same if your a value is negative, right? You're going to have a graph that is upside down, you're going to have a graph that is upside down, or you're going to have a graph that is upside down. It either cuts through here and here, doesn't cut through and just sits right on it, or doesn't even cut through at all. So exactly the same, just with a negative a value. Now, this entire section is about graphing parabolas. So I hesitate to say this is easy, but once you start doing it, rather than plugging in, I'm going to try and demonstrate to you a more intuitive, but also more, I don't know the word here I want to use. It shows a level of thinking and a level of understanding that is a little bit more superior than just the plug and play. So that's my whole point, is that's the level I want to get you at, right? So 1, identify your vertex and your axis of symmetry, because if you can graph one side of the axis of symmetry, it's just a mirror image on the other side. 2, get your y-intercepts and your x-intercepts, because it's nice to have points that we know are going to be on our graph. Any additional points, and then just do a rough sketch. If you have the vertex, you have some intercepts, you're okay. This thing doesn't need to be absolutely perfect at this point, but you can't screw up those points. So I'm going to break this down into a few different examples. So AX and then changing the A value. Now what you got to look at is this. First, I want you to look closely at these graphs because they're not one per every grid, right? It's 1, 2, 3, 4. And 1, 2, 3. So every 2 represents 1. So help your brain kind of tune into that. And I mentioned it earlier on here. If you have a positive A value, opens up, vertex is a min. If you have a negative A value, opens down, vertex is a max. Okay, now you're going to have a wide parabola, so stretched out parabola. If your A value is in between -1 and +1, which means what? It means it is a fraction, either positive or negative, right? And you're going to have a steeper parabola, skinnier parabola, a more narrow parabola if A is greater than 1 or if A is less than -1. Now, if it's 1, you're just going to have this most basic. So I want you to look closely at the most basic because here's where I get the extra detail from. When A is 1, you're dealing with y equals x squared. So just think about this. You're plugging in a value for x, you're solving for y. I'm just going to do a little table of values up here. You can see what happens, okay? This is for y equals x squared. When x is 0, y is 0. Boom, there's our vertex, right there. Now, when x is 1, y is 1 squared. So 1. But when x is -1, y is also 1 squared. You see, there's the symmetry. Now, when x is plus or minus 2, so if it's positive 2, y is 4. If it's -2, y is 4. So you're going to go 2, 4. So here's where my piece of thing, and then what's 3, right? 3 plus or minus 3, we're up 3 squared, 9. Now that's off my grid. But here's what I want you to think. From your vertex, your basic parabola goes over 1, up 1. Your basic parabola goes over 2 from the vertex, up 4. And then it's going to go over 3 from the vertex and up 3 squared to 9, right? So it's over 1, up the square version of however many went over. Over 1, up 1. Over 2, up 4. Over 3, up 9. Over 4, up 16. And you'll see where this comes from and how this relates, because it directly relates to your A value. If you look at the next one, A equals 3, we're going to have a steeper, narrower graph. Now, for the original, it was over 1, up 1. But if you're multiplying x by A, whatever you go over, multiply that by the A. Or sorry, whatever you go up, multiply that by A. So in the basic, it's over 1, up 1. We should be there, right? That's a basic graph. But A is 3. So you're multiplying your y value by that 3. So instead of over 1, up 1, it's over 1, up 3. Boom. And then instead of over 2, up 4, it's now over 2, up 4 times 3, 12. And you see, I'm not even on the grid. 12 is way up here. It's way skinnier because it goes up way faster, right? Now you could plug it in, don't get me wrong. If A was 3, you'd have y equals 3x squared. Plug a 1 in, 3 equals 1 squared, 3 times 1, y is 3. If x was 2, it's that. So y equals 3 times 4 equals 12. So you'll get there too, plug and play, no problem. But what I'm trying to get to is, if you have a simple graph like an ax squared, multiply your output, your y value, by whatever the a value is. Okay, let's look at that again in this next one. A is 1/3, so multiply your output. So if we think over 1, up 1, we're now over 1, up 1/3. And then normally it's over 2 up 4, but 4 times 1/3. So now you're going to go up 4 1/3. So you're going to see over 2 up 1 1/3, which is why we're there. And then over 3 up 9, well, that's nice because you have a denominator of 3. So up 9 becomes 9 times 1 over 3, which is up 3. So if we go over 3, we're actually up at 3. And you can see this pattern start to emerge. Now, I don't expect you to get this right off the bat. I don't expect you to get this necessarily at all. If you are a plug and play kind of person, go for it. This is just a little bit of thinking to a, I don't want to say a higher level, but a more intuitive level, a more visual level, an understanding of the equation to a bit higher, right? Pushes you into that mastery level. So here, a is just negative. Right, this next example right here, -1. So what we do, we've taken our y equals x squared grid and we've just flipped it over. Now, I've also messed with you a little bit because you can see the scale of this graph is 1, 2, 3, 4, 5. So we don't have it stretched out. So this is still over 1, but instead of up 1, it's down 1 because it's been reflected. Over 2, down 4. Over 3, down 3 squared to 9. Over 4, down 4 squared to 16, right? Like we're going to be there. Same pattern. Now here a is -2. So you're going to be flipped into the negatives and you're going to be stretched. Instead of over 1 up 1, it's over 1 down 2. Over 2, instead of down 4, we're going down 8. Instead of over 3 and up 9, it's down 9 times -2 to -18, right? You're going to be like way down here. Now here a is -1/2, so everything's going to be flipped. Instead of over up, it's over down. So instead of over 1 up 1, it's over 1 down 1/2. And then over 2 down 4 becomes over 2 down 1/2 of 4, which is 2. Over 2 down 2. And then 3 to 9 gives us an odd one, but if we wanted to go to 4, 4 should take us to 16, right? 4 squared, 16. But we're going down 16 times -1/2, so 16, we should go down 8. And we have. But again, you can just plug these in. Y equals -1/2 times x squared. So if x was 4, right, squared. So y equals -1/2 times 16, which is -8. You'll get there that way. Just trying to show you a different way of looking at it. Now, I'm not going to do every example here moving forward. You can look at them yourself because I don't want this lesson to be 40 minutes on here. I'm going to try and keep it, but we're looking at this now. So this a value, what did that do? A value either made it narrow or wide. But now we're looking at this plus c. Now what you'll notice, it is apart. It is outside of the square portion. You'll see what I mean by that in this example down here. It's not included in the square. C is a shift up or down. And it's really straightforward. If C is a negative number, so here if C is a positive number, it's vertically up. If C is a negative number, it's vertically down. So honestly, probably the easiest shift you're going to do. Here, y equals x squared plus 1. So you basically take your regular graph, your over 1, up 1, over 2, up 4, over 3, up 9, but everything gets shifted up 1. So instead of your vertex being at 0, 0, your vertex is at 0, 1. Instead of your point being at over 1, up 1, we're now over 1, up 2. And watch the scale on your grid again. It's changed here. Over 1, up, you're still over 1, up 1, but the whole graph's been shifted up. You're still over 2, up 4, but your coordinate is 2, 5 instead of 2, 4 because your whole grid has been shifted up 1. Same sense here, except the whole grid has been shifted down. So instead of starting at 0, 0, we start at 0, -1. Instead of going over 1, up 1, we're going over 1, up 1. But we're starting from a lower point. So just all your points on your basic get shifted down. So you could even think, I'm going to graph my basic graph and then just shift everything down. Here, we have an example of a double shift. So your A value and your vertical. So This is where you get into, it might make a little bit more sense for your brain right now to plug points in. So if let's just do, and I'm going to consider symmetry, so I'm just going to go to the right of my graph. So I got x and y. X is, my vertex doesn't shift anywhere, so I'm not even going to bother. X is 0, x is 1, x is 2, x is 3. So when x is 0, well, what happens to the negative 1/2 x squared? It's 0 plus 1. Now, I don't like necessarily to use numbers like 1 because it can make your values a little bit more confusing, but let's give it a whirl. When x is 1, what's 1 times negative 1/2? Well, negative 1/2 plus 1 is 1/2. Now when x is 2, 2 squared is 4. 4 times negative 1/2 is negative 2. And then I'm adding 1. 4 times negative 2. Then I'm adding 1 to negative 1. And then don't worry about x is 3, but we'll go from there. And you'll see, when x is 0, I'm at 1. Now, again, watch this scale on your grid, right? There's 1. There's 1. There's negative 1. So when x is 1 here, I'm at 1/2. And this is 1/2 because that's halfway to 1. And then when x is 2, I'm at negative 1. And there it is, right? So it's following that trajectory. So this might be a plug-in scenario. If you can do it in your head, great. If you've got to write it down, please write it down, right? Like, be as consistent as you can with it. But if you have a shift that comes outside of the x squared, so you're not multiplying with the x squared, it's not in with the squared, it happens after, it's a vertical shift. If it's happening inside, so you'll see here what I mean by that. Happening inside, so it's acting on x before the square, it's a shift left or right. Now, this is going to be a little paradoxical, oxymoronic, however you want to say it. Here it's x minus 2, but I'm shifting to the positive direction. And here it's x plus 3, and I'm shifting in a negative direction. So some people will say, if c is greater than 0, shift right. If c is less than 0, shift left. Fine, but honestly, the easiest way for me to think about this is what's happening to my vertex. What value of x makes y equal 0? Because if you think this is a horizontal shift, you're not worrying about the up and down. Your basic parabola, the vertex is on the x-axis, right? There is 0 y shift. So if you can make this whole thing equal to 0, that's where you've shifted left or right. So what makes this equal to 0 when x is 2? Because 2 minus 2 is 0. And look, x is 2. What makes this 0 when x is negative 3? Well, look, we're at negative 3. What makes, and forget this. This doesn't even matter. What makes this 0 when x is 2? Right there. So whatever makes the inside portion equal to 0, that's which direction you've shifted. Whatever x value makes it equal 0. So if x is positive 2, like the first question, you're at positive 2. You don't have to worry about, oh, do I shift left or right? No, what makes it 0? If x is a negative number, it's on the negative side. If x is a positive, it's way easier to remember, way easier to think. All right, now we're going to start putting it together. What happens if we have everything happening, all the shifts? This is what we call standard form. So the first one was general. Okay, this is your standard form. The vertex is the value of h and the value of k when, and this is big, there's a negative sign. Okay? It's when there's a negative sign. So if we look at this first example, standard form is x minus. Oh, look at that, x minus. So what's the value of h? Positive 1. What's the value of k? Negative 3. That right there is your vertex. 1 comma negative 3. 1 comma negative 3. Right? Now, if you wanted to look at it the way I just explained it a second ago, you have x minus 1 squared minus 3. And we said that it's h when you're in the form x minus 1. But you can also think it's just whatever makes that equal to 0. So again, x is 1. That's my horizontal shift. 1. And then vertical shift is your vertical shift, down 3. Here, a term does not matter when we are graphing the vertex shift. Now, when we were graphing whether or not it opens up or down, right, that's when the a matters. But we already talked about that. Here, the a value is positive, we opened up. Here, the a value is negative, so you know you're going to open down. Well, what happens to your vertex? What makes this 0 when x is negative 1? And then plus 2. So my vertex has gone to negative 1 plus 2. What makes this 0 when x is negative 2? And is there a vertical shift? No. So you've just moved negative 2. Again, this opens up 1. So I'll say it again. This is something you're going to have to watch more than once. This is something you're going to have to read more than once. This is something you're going to have to practice a lot. But it's important that you get this, because it's everything we do in the next few sections is going to build. Domain and range we've talked about in grade 10 briefly, but for a refresher, the domain is every possible x value that the graph can include. The range is every single y value that the graph can include. Now, if you're given a set of ordered pairs, like these 3 examples here, the domain is the x values. Negative 3, 1, and 4. The range is the y values. Negative 2, 2, and 5. Look at B, and then I'll let you look at C and D on your own. Negative 3, 1, 0, 3. So, boom. Domain. The range is your y values. If you have repetition, you'll see here there's some repetition. You only include it once, because it's already there. You don't need to put it in twice. All right? So domain and range. So now here, example. Determine the domain and range of the following parabolas. I'll give it to you right now. Domain for a parabola is always all real numbers. All real numbers. All real numbers. Because your parabola, it may look like it's going to open steeply like this, right? It's going on forever. It's going on forever. You're like, well, how is it ever going to get to negative infinity? Because it will. It will very slowly get there. And yeah, by the time you're up to here, it might only be at negative 4. But you got to remember, infinity is a concept. This graph continues forever. It will eventually extend infinitely in the negative direction and infinitely in the positive direction. So the domain is always all real numbers for a parabola. The range is, well, what's my minimum or my maximum point? And do I open up or down? Because here you're going to have a whole bunch of y values that are never going to be included, but all of these ones will. So it's everything greater than or equal to the minimum point. So here, what's the minimum point? It's negative 3, right? So it's greater than or equal to negative 3. Here, my maximum point is positive 2. And since I'm opening down, it's everything less than or equal to positive 2. And then here I'm sitting right on the axis. So it's everything greater than or equal to 0. So range is an easy one. Domain is an easy one too. So the domain and range of parabola is game on. So that's how domain and range work for a quadratic. The domain is always all real numbers, and the range is either the lowest or highest point. And then if it opens up, it's everything greater. If it opens down, it's everything less. So now how do we graph a full equation? Now you'll notice I didn't leave anything blank. I'm just going to go through them with you guys. So because you can graph them using plug and play, or you can graph them using my over 1 up thing. So I'll kind of show you both right now. So if we use plug and play, right, here's the example, and they've given us the vertex. It is a minus, but also, what does x have to equal in order to make that inner portion 0? X is 1. And then I'm on highlighter, so bear with me. X is 1. And your shift down, negative 3. So that's your vertex, right? And I have it right here. So plot your vertex, boom. There it is. Now if you want to plug points in, you can see I did that up here. Okay, so next I picked one to the left and one to the right of my vertex. So I plugged x equal to 0 right here. Right, plugged it in, and you solved, and y was -1. So you have a point at 0, -1. Now, if you take one point to the opposite direction of the vertex, so that was to the left, and then this will be to the right, you'll see I also get -1. And you should expect to get that because the line of symmetry that goes through the vertex, right? It's symmetric on both sides. So if I have a point here, I should have a point here. And if I have a point here, I should have a point here. Now I found those by plugging points in and trying. And you'll see max, min, I have a minimum value of -3. It's my lowest point. My axis of symmetry is a vertical line through the x value of my vertex, right? So that is my axis of symmetry. That is my minimum value. And then domain, all real numbers, and range, everything greater than -3 because I open up. But now I'm going to show you my over 1 up. So just think basic, right? What's your basic graph? It's over 1 up 1, right, over the square. And then it's over 2 up the square, 4. And then over 3 and up the square, which is 9. And then over 4 and then up the square, which would be 16. But you have to consider your a value. The a value of this graph is a 2. So instead of going over 1 up 1 here, right, we'd go over 1 up 2. And we'd go over 4 up 8. And then you go over 3 up 18. And you go over 4 and up 32. Because you are doubling the output value. And you'll see that happens here. We go over 1 up 2. Over 2 up 3, 4, 5, 6, 7, 8. So you could also graph it that way rather than plugging in. If you get really comfortable with your a value, be like, oh, over 1 up 2, over 2 up 8, over 3 up, and it's easier. And then you have your symmetry, right? It's still over 1, over 2, and you could graph it that way. Totally up to you. I highly, highly recommend trying to get as comfortable with that as you can. I think there's one more example, and then I think we're about there. So again, vertex first. So I know my x value in here is going to need to be -2, and I've gone up 4, so boom, there's my vertex, -2, 4, right there. My a value is a negative. So all that really needs to tell you is you're going down instead of up. Your a value is also a half. So if you're going over 1 up 1, you're now going over 1 up, except down, sorry, because it's negative. Over 1 down a half. And then normally you'd go over 2 and up 4. We're going over 2 and down 2. And then 3 I'm not going to bother because it's not a multiple of 2, so I can't divide it nicely with the half. But then I'll do 4. I would go over 4. Normally I would go up 16. I'm going down 8. Now here, I did plug and play. So if you like plug and play, have a look, right? If I go over 1, if x is -6, right, I end up here. If x is -4, I end up here. Boom, and there's my symmetry. But if I go the other way, here, and again, watch the 1, 2, 3, 4, 5. Always careful to check your scale of your graph. But look, over 1 down a half, that's not necessarily easy to graph. So I'm going to jump right to this. If I go over 2, I should be going down 2. Oh, would you look at that? And then if I'm going over 3, right, I didn't put that in because, again, you're going to end up with probably a fraction to graph. So let's go to this one. Over 4, down 8. And there it is. So try to get used to that or just plug it in and you will get your symmetry. It's totally up to you. You got your vertex, now this time it's a maximum because it opens down. We got our axis of symmetry, domain, range. That's where you're going. Okay, so the rest of the booklets for you to work on. There's a lot of questions to practice your graphing. Please, 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 please practice your graphing. However way you want. Try to get used to both. Watch the video or snippets of the video a few times. Read your notes. Try, right? I know this at-home learning is tough, but this is the boat we're in right now, so let's make the best of it, okay? Your guys' Unit 3 work looked great. And if this is a new video for you and you didn't do Unit 3 yet, or you haven't given you marks yet, I'm sure it looks great. Okay, have a great day, you guys, and I will see you next video.